All right, so I would like to begin by reminding everyone that an Einstein metric is by definition a Riemannian metric of constant Ricci curvature. And that's equivalent to saying that the Ricci tensor is a constant multiple of the metric. The metric here is denoted by H. R is the Ricci tensor, and we're assuming that for some constant lambda, the Ricci tensor is lambda times the metric. This is called the Einstein condition, but actually Einstein called this the greatest blunder of his life. When he introduced the constant lambda called the cosmological constant, he was trying to fudge something in cosmology and came to the conclusion it was a bad idea. Here he is a few years later, definitely wishing he had never suggested the possibility that the Ricci curvature might be a constant lambda other than 0. And as punishment, we therefore call lambda the Einstein constant. It has the same sign as the scalar curvature, which is the trace of the Ricci tensor. Specifically, the scalar curvature would be lambda times the dimension of the manifold. And in this lecture, the dimension of the manifold is going to be 4 for almost the entire lecture. So there's a basic recognition problem associated with the study of Einstein metrics. The real question is, are Einstein metrics good for anything? If you have an Einstein metric on a smooth, compact N-manifold, does it tell you anything about the manifold? Can it help you identify which manifold you're looking at or which class of manifolds you're looking at? So can you recognize the manifold by looking at an Einstein metric on it? In low dimensions, the Einstein, so for example, in dimension 3, an Einstein metric is actually a metric of constant sectional curvature, and the whole Ricci flow program for solving the Poincare conjecture in dimension 3 for geometrizing 3 manifolds was based on trying to find Einstein metrics on 3 manifolds, because in dimension 3 they are metrics of constant sectional curvature. If you have a compact manifold with constant sectional curvature in dimension 3, its universal cover would have to be the standard 3-sphere or Euclidean 3-space or hyperbolic 3-space, maybe after multiplying the standard metric by a constant. On the other hand, in high dimensions, if the dimension is at least 5, it looks like the situation is pretty hopeless. So for example, it is known that on the N-sphere for N at least 5, there are many, many non-standard Einstein metrics. It's known that, I think in dimension 5, that there are thousands of connected components. And if you were given a little piece of one of these metrics, you could just see a little piece of the manifold, you would have probably no idea that you were on a sphere. So in high dimensions, even though Einstein metrics are very, very interesting, they're not necessarily very good for solving problems linking geometry to topology. On the other hand, in dimension 4, the situation is much more encouraging. So if we introduce the so-called moduli space of Einstein metrics, we take Einstein metrics via modulo the action of the diffeomorphism group and also of the positive constants by rescaling the metric, then this is known for certain 4 manifolds. So for example, if M is the 4 torus, Berger showed that any Einstein metric on the 4 torus had to be flat. Hitchin showed that any Einstein metric on K3 has to be a Calabi-Yau metric, and he actually proved that before Calabi-Yau metrics were known to exist. It was before Yau's solution of the Calabi conjecture, but it eventually leads to the conclusion that we actually completely understand the moduli space of Einstein metrics on K3. Another class of manifolds would be the compact real hyperbolic 4 manifolds. Those are compact quotients of real hyperbolic force space by discrete subgroups of the isometry group. And Besson, Courtois, and Gallot showed that any such metric in dimension 4 had to be the standard metric up to rescaling. There's actually only one metric. The moduli space here actually turns out to consist of a single point. And then I also showed the same was true of another class of locally symmetric spaces in dimension 4, namely quotients of the complex hyperbolic plane, or if you like, the unit ball in C2. These uniqueness results actually turn out to be related to various non-existence results. So many four manifolds, in fact, in some sense, most four manifolds do not admit Einstein metrics. And to illustrate this point, I want to show you a more extreme version of this conclusion. Suppose that we look at, so Einstein metrics could have positive Einstein constant or negative Einstein constant or zero Einstein constant. Let's suppose we look at Einstein four manifolds that have lambda greater than or equal to 0. And I want to make an extra assumption about the four manifold. So if we assume that we're looking at a smooth, compact-oriented four manifold that also admits a symplectic structure, and that's to say it admits a closed non-degenerate 2 form, then it also admits an Einstein metric with lambda greater than or equal to 0, if and only if M is on the following list. So here, we're assuming that there's an Einstein metric. We're also assuming that there's a symplectic structure, but we don't assume that there's any local relationship between these two objects. It's like they live in the same apartment building, but they've never actually met. All right, so the first family of manifolds which have these properties, there's a symplectic structure and there's also a lambda greater than or equal to 0 Einstein metric, would be the connected sum of CP2 and K CP2 bars, where K is an integer from 0 to 8. So if it's 0, we just mean CP2. At 8, it would be CP2 connected sum 8 CP2 bars, where CP2 bar means CP2 with the non-standard orientation, and the hash sign is the connected sum. It means that you take two given oriented manifolds, you throw a ball out of each one, and you glue them together to make a connected manifold, just the same way that you would build up a genus 2 surface from two tori. All right, so so the list begins with CP2 connected sum K CP2 bars, where K is between 0 and 8. The next thing on the list is S2 times S2. Then I mentioned the manifold K3 in a moment ago. So K3 arises as a simply connected complex surface with vanishing first Chern class. There's only one diffeomorphism type of K3. By the way, K3 it stands for Kummer, Kähler, and Kodaira. That's terminology invented by André Weil. So a typical model is you could take a smooth quartic hypersurface in CP3, and that is an example of a K3 surface, and any other K3 surface is diffeomorphic to that model. All right, so then it turns out that K3 is a double cover of another manifold, K3 mod Z2, and the 4 torus is another object on this list. Obviously, it has flat metrics, and Berger's theorem is going to say that those are the only Einstein metrics on the 4 torus. And then there are certain quotients of the 4 torus by certain finite groups acting each one in a standard way, preserving the flat metric. So you take an R4 mod some lattice, and then you have an action by certain finite groups of isometries. So that's a complete list of 4 manifolds that admit Einstein metrics with lambda greater than or equal to 0, and which also admit a symplectic structure. So there are 2 assertions here. Each of these manifolds admits a lambda greater than or equal to 0 Einstein metric. course, as soon as you have one, you can at least rescale it. You can pull it back by diffeomorphisms, but there's still the more general moduli problem to ask. But the other thing is that with these hypotheses, there are no other candidates. So this is a complete list of candidates for carrying such metrics, and every candidate actually does have such metrics. Since this is a conference with an emphasis on almost complex structures, well, if you put a complex structure, and you might want to suppose you had a complex structure rather than a symplectic structure, and actually the theorem is a little bit easier there. It's easier to use, surface classification narrows down the candidates very quickly, whereas if you assume there's a symplectic structure, you need a little bit more modern technology. All right, so the things that occur here all do admit complex structures. They arise, the things on the first line and on the second line together make up the family of complex surfaces called del Pezzo surfaces. At least here we've only listed the diffeomorphism type. Then there's the K3 surface. The next one is the Enrique surface. Then there is the so-called Abelian surface. The so-called Abelian surfaces are C2 mod lattices. And then there are various complex surfaces that can be displayed as elliptic curve bundles over an elliptic curve, and those are the so-called hyperelliptic surfaces because they were first discovered in the context of the study of hyperelliptic functions. So all such results depend upon the special character of dimension 4. So on an oriented 4-manifold, with a Riemannian metric, you can split the two forms up as a sum of two rank 3 bundles, the so-called self-dual and anti-self-dual 2 forms, which are by definition the eigenspaces of these subspaces of the 2 forms are the eigenspaces of the Hodge star operator, which has eigenvalues plus and minus 1. So also, it's an interesting point. This splitting does depend on the metric, but it's conformally invariant. If you change the metric just by multiplying it by some function, then you still have the same splitting of the 2 forms into self-dual and anti-self-dual pieces. So this decomposition of the 2 forms also allows you to decompose the curvature tensor of a 4-manifold into pieces, because one way of thinking about the curvature tensor is it's a map from 2 forms to 2 forms. It happens to be self-adjoint. This then splits into 4 irreducible pieces, because you have a piece that maps self-dual 2 forms to themselves, and a piece that maps anti-self-dual 2 forms to themselves, and so forth. This here, if you think about this as a matrix, it's a symmetric matrix because of the first Bianchi identities. All right, so in fact, the scalar curvature, which is one of the most basic invariants, part of the Ricci curvature, appears in this picture as a multiple of the identity. The trace-free part of the Ricci tensor shows up as the off-diagonal block, and these 2 blocks are really the same. They're transposes of each other. Then there are 2 remaining pieces of the curvature operator, the so-called self-dual Weyl curvature and the anti-self-dual Weyl curvature. And while these might seem a bit mysterious at first, the key property that they both share is that they're both conformally invariant. When you multiply a metric by a function, it changes the Ricci tensor in terms of, by adding on expressions that involve 2 derivatives of the function you've multiplied by, whereas W plus and W minus don't change. All right, well, strictly speaking, in this way of representing them as parts of the curvature operator, they do carry a weight. They're multiplied by a certain power of the function you've multiplied the metric by, but actually intrinsically, in terms of the usual you can display them as pieces of the full curvature tensor in such a way that they're literally unchanged by multiplying the metric by a function. All right, so one standard tool that comes out of this picture that's, so for many of you, I'm telling you things that you know very well, but I want to make the lecture as self-contained as possible. So if you have a compact-oriented Riemannian four-manifold, one interesting invariant you might look at is there's a bundle lambda plus over the manifold of rank 3. You could ask what's its first Pontryagin class. And that's basically a number because it's an element of H4. You can integrate it on the manifold. When you do that, you think of the first Pontryagin class of lambda plus in that way. It's just twice the Euler characteristic plus 3 times the signature. So there are a couple of basic invariants of a four-manifold. The Euler characteristic, the signature is B plus minus B minus, where B plus and B minus are respectively the dimensions of maximal subspaces of the second cohomology on which the intersection form is positive or negative definite. And it turns out that the signature is actually the first Pontryagin class of the tangent bundle over 3. So this invariant is very prominent when you look at almost complex manifolds. If you choose an almost complex structure that is compatible with a given orientation on the manifold, then C1 squared of the complex structure actually turns out to be just a different way of describing the first Pontryagin class of lambda plus. On the other hand, there are Gauss-Bonnet type formulas for the Euler characteristic in the signature, or you could just say what would be the curvature representation of an integrand for P1 of lambda plus, and you'd find out that it involves the scalar curvature squared and twice the pointwise norm of W plus squared minus the trace-free Ricci curvature squared. That was simply what will fall out if you use the connection on lambda plus that's induced by the Riemannian connection. The cute point is that if your metric H happens to be Einstein, the only negative part of this integrand drops out, so the integrand is actually pointwise non-negative. And that immediately tells you that if you have an Einstein metric on a four-manifold, then 2 chi plus 3 tau of the manifold has to be non-negative. By the way, you could also reverse the orientation of the manifold. The Einstein condition is invariant under that, but that would change the sign of the signature in this expression. But here we're going to imagine we're privileging a particular orientation, and this is now the interesting inequality, or the one that will be most relevant to what we're doing. So it's saying that if there's an almost complex structure, it'd be saying C1 squared of that almost complex structure would have to be non-negative. And it could, you only get equality here if the Riemannian connection on lambda plus is actually flat. And then, as was first pointed out by Hitchin, first of all, Hitchin observed that this was what happened when the equality was saturated, when the inequality was saturated, but also then pointed out that that would mean that the manifold was finitely covered either by a 4 torus or by a Calabi-Yau K3. All right, so I gave you a list of smooth compact four manifolds that admit both a symplectic structure and an Einstein metric with lambda greater than or equal to 0. And the surprise is that there aren't very many of them. It's a definitive list. It kind of comes up with various hypotheses. On the other hand, there are cases here we understand much better than others. So I've just drawn a red line, and below that red line, every Einstein metric is actually Ricci flat and Kähler. It's actually a Calabi-Yau metric. On the other hand, in particular for this class of manifolds, the moduli space is completely understood, and in fact can be shown in particular to be connected. So all the Einstein metrics on the manifolds below this red line belong to a single connected family. Above the line, we do know that each of these manifolds admits an Einstein metric. So the moduli space is definitely non-empty. But the main question I'm going to be discussing in this lecture is this moduli space connected? So the objects that were above that red line arise in complex geometry as del Pezzo surfaces. In other words, these are the compact complex surfaces for which the first Chern class is also a Kähler class. This is often written in a shorthand as C1 greater than 0, and that confuses every student beginning in the subject. It's important to realize that this is not an inequality of numbers. It's a partial relation on cohomology classes. C1 is bigger than 0 in the sense that it's gotten from 0 by adding a Kähler class. All right, so the classification of these is very standard. The main possibilities are that you take CP2 and you blow it up at K points in general position, where K is some number between 0 and 8, or CP1 times CP1. So, for example, if you take CP2 and blow it up at 3 points where the 3 points are not on the line, then that would be an example of a del Pezzo surface. Now, blowing up is a process where if you start with a complex surface, you can replace any point on it with a CP1, whose normal bundle is the Chern class -1 line bundle over CP1. And the effect that that has on its differential topology is that it's taking the connected sum with a CP2 bar. The reason is that CP2 bar minus 1 point is actually, can be thought of as the O-1 line bundle over CP1 as a smooth manifold. CP2 bar does not have a complex structure that's compatible with its orientation, but if you throw out a point, that's no longer true. So the picture is that in C2, you can replace the origin with the total space of the O-1 line bundle, the tautological line bundle over CP1. Usually you can think of that as a subset of C2 times CP1, but now you could just look at the projection to C2, and that's blowing down the 0 section to a point. Using that as your local model, you can carry out this blowing up procedure at any point of any complex surface. All right, so I said that the del Pezzo surfaces are the blowups of CP2 at 0 to 8 points in general position, or CP1 times CP1. The general position statement is that no 3 of the points are on a line, no 6 of them are on a conic, and no 8 are on a nodal cubic with one of the points at the node. So these are the obviously necessary conditions. They're necessary in order to avoid having a CP1 of self-intersection -2 or something more negative in there, because then C1 couldn't possibly be represented by a Kähler class, just by a junction. All right, so here is the basic theorem that relates this subject to Einstein metrics. Each del Pezzo surface, and now we're thinking of it as not just a 4-manifold, but it's equipped with a particular complex structure for which C1 is positive. Each del Pezzo surface admits a J-compatible, conformally Kähler Einstein metric. And here I said conformally Kähler. These are not all Kähler metrics. So conformal geometry, remember, has to do with taking a metric and multiplying it by a function. Once you're in complex dimension 2, that steps immediately out of the Kähler realm. So if you multiply a Kähler metric G by a function f squared, and it's just conventional, it's useful to write it as f squared rather than f, you get another metric which would be said to be conformally Kähler. So, so in this setting, the related metric, G is a Kähler metric, we've multiplied it by some function, the new metric is said to be conformally Kähler. If an Einstein metric is conformally Kähler, in dimension 4. That imposes, so the Einstein equation implies a conformally invariant condition called the vanishing of the Bach tensor. So the metric is Bach flat. And one consequence of this for a Kähler metric is it immediately implies the Kähler metric is an extremal Kähler metric in the sense of Calabi. In other words, the gradient of its scalar curvature, thought of as a vector field of type 1, 0, is actually a holomorphic vector field. All right, so if the 4-manifold is actually compact, it has a conformally Kähler-Einstein metric, but it's not Kähler-Einstein, then you can actually show that the scalar curvature of this extremal Kähler metric is positive, and the Einstein metric has to be of the special form that it's the extremal Kähler metric times the inverse square of the scalar curvature times a positive constant. This was a fact basically discovered by Dzerzhinsky, which didn't get very much attention at the time. In fact, Dzerzhinsky didn't know about Calabi's work on extremal Kähler metrics, but it turns out that it's a key to understanding the problem. So every del Pezzo surface admits a J-compatible conformally Kähler Einstein metric, and this metric is actually unique up to complex automorphisms of the complex surface and constant rescalings. So if you could normalize the metric by setting the Einstein constant equal to, say, 1 to get rid of the freedom of constant rescaling. It turns out they all have positive Einstein constants, and most of them are actually Kähler-Einstein. I'll say that the metric it's not quite unique because some of these surfaces have non-trivial complex automorphisms, and the really important ones are the ones that are in the identity component of the automorphism group. So that turns out to be a source of non-uniqueness in the most obvious sense. But in terms of the isometry type of the metric, it's actually the same metric, just moved by a very special kind of diffeomorphism and then rescaled. So I'll just say that the metric is geometrically unique. So in terms of existence, the first non-trivial example was CP2, the Fubini-Studi metric, or S2 times S2 with 2 round metrics of the same radius. Those are classical. Who would you attribute these Einstein metrics to? Who first noticed that they were Einstein? I don't know. But the first really kind of non-trivial example was found by Page in 1978. Page is a physicist, a student of Stephen Hawking, and he wrote down a particular Einstein metric on a compact 4-manifold that turns out to be CP2 connected some CP2 bar. And Dzerzhinsky in 1983 then discovered that Page's metric is actually conformally Kähler, and discovered that the Kähler metric it was conformal to had some remarkable properties. It's in fact, we'd say it's an extremal Kähler metric in the sense of Calabi. Calabi wrote his paper on extremal Kähler metrics that same year. In 1986, Hsu proved that CP2 blown up at 3 points has a input general position, has a Kähler-Einstein metric. Tian and Yao the next year showed that for each del Pezzo surface diffeotype, well, actually for the deformation type, there are certain complex structures, del Pezzo type, where there are Kähler-Einstein metrics, except in 2 cases that were excluded. CP2 connected some the 1 or 2 point blowups of CP2. Just seeing that Page had discovered a conformally Kähler metric on CP2 blown up at 1 point. Then Tian published a paper in 1990, which is the one that's usually attributed the statement that except for the 2 excluded types, there's a Kähler-Einstein metric on each of them. Tian actually did many, some of the cases are correctly done. There are other cases in this paper which turn out to be wrong. It's a difficult paper to read. Tian's basic approach works. Odaka, Spotty, and Sun wrote a very careful reproof in 2016, which follows Tian's original ideas, but implements all of the details correctly. And then before that, with Xueshong Chen and Brian Weber, I had discovered that on CP2 blown up at 2 points, there was a a conformally Kähler Einstein metric. The uniqueness statement that there's only one such metric, for the Kähler Einstein case, for example, if you're looking at Kähler Einstein metrics on P2 blown up at 3 points in general position, that follows from a theorem of Bondo and Mabuchi from 1987. For the case where the metric is not assumed to be Kähler Einstein, then the uniqueness was something I proved in a paper in 2012. All right, so the basic problem is to understand all Einstein metrics on del Petzos. We've seen that every one of those del Pezzo diffeotypes carries some Einstein metric with positive Einstein constant, in fact. But what is the moduli space? Is it actually connected? So this is still an open problem. The progress to date, and I'm going to tell you about some new developments, is that there are some now nice Riemannian characterizations of the known Einstein metrics, the conformally Kähler ones. And in particular, one knows that these metrics are actually represent exactly one connected component of the moduli space. So that was actually first proved for all cases in a paper I wrote in 2015. On any del Pezzo four manifold, so I'm talking about the underlying four manifold, not the manifold endowed with a particular complex structure. The conformally Kähler Einstein metrics are exactly characterized by the fact that their self-dual Weyl curvature is everywhere positive in the direction of some non-trivial global self-dual harmonic two form. And because that's an open criterion, I was able to then show that in fact, the known Einstein metrics sweep out exactly one connected component of the Einstein moduli space. So I found this a reasonably satisfying result at the time, but there is something a little bit disquieting. W plus omega omega is positive as not a purely local condition because the omega we're talking about is not an arbitrary self-dual two form. It's supposed to be a global harmonic two form. It turns out that on self-dual two form, on a del Pezzo surface, there is exactly one such thing up to a multiplicative constant. So you're using something global mixed in with a local thing, curvature. A young Chinese mathematician named Peng Wu then came up with a different characterization, which I think is really a terrific insight. He uses only a purely local condition on the self-dual Weyl curvature. So the self-dual Weyl curvature of a Kähler manifold, W plus is by definition the trace-free part of a piece of the curvature tensor, the part that maps lambda plus to lambda plus. But that's spanned by the Kähler form and the real and imaginary parts of holomorphic two forms on a Kähler surface. So in fact, you can then show that W plus has two equal eigenvalues minus the scalar curvature over 12 and one other eigenvalue, scalar curvature over 6. And in particular, its determinant is everywhere positive. If you have a metric which is conformally related to a Kähler metric of positive scalar curvature. And of course, this is a conformally invariant condition. If you multiply the metric by a function, it just multiplies the determinant of W plus by a power of that function. So this is actually a conformally invariant characterization. So Wu's criterion is to demand that the determinant of W plus be everywhere positive. And in 2019, Wu came out with a very short, difficult to read paper, which asserts that that not only is this a necessary condition, it's also sufficient. Because I had a hard time understanding his proof at first, I decided to check it by finding a completely different proof of my own. And my own proof, which I'll describe a little bit, actually proves more general results. And I'll also be briefly discussing a more recent paper which gives some related classification results. All right, so the first main theorem is, suppose you have a compact-oriented Einstein manifold, and let's assume that it's simply connected, and suppose that its self-dual Weyl curvature has positive determinant at each point. So this, remember, the self-dual Weyl curvature is a linear map from lambda plus to lambda plus, and so it makes perfectly good sense to say what's the determinant of that transformation. And then the statement is that H is conformal to an orientation compatible Bach-flat extremal Kähler metric with scalar curvature positive on the manifold. And in fact, this is exactly the class of Einstein manifolds I was discussing before, but now we're not starting off by assuming that the metric is somehow compatible with a complex structure. We're just saying that its curvature tensor has satisfies a certain property. So let me give you in a more concrete sense, what are we saying about the eigenvalues of W plus? Well, if the determinant of, we could diagonalize W plus to have eigenvalues alpha, beta, and gamma, where I'll take alpha to be the largest one, gamma to be the smallest one. Unless W plus is 0, alpha has to be positive and gamma has to be negative because the trace is 0. All right, so that ends up saying the determinant is alpha, beta, gamma, so that means that the determinant has the opposite sign from the middle eigenvalue. To say that the determinant is positive is the same as the middle eigenvalue is negative, so that, if you like, W plus has a kind of Lorentz shape, one positive direction and two negative directions at every point. In particular, that means that the positive eigenvalue has multiplicity 1, and therefore it actually defines a nice smooth function on the manifold. And then you might say, well, let's choose a two-form, a self-dual two-form, which is an eigenvector of W plus, and we can normalize it, for example, to have pointwise norm square root of 2. But then if you look at it, you might realize that in the process, so a priori there are two such omegas at every point, and you've either defined this omega on M or on a double cover. So if you might only get this on the double cover, but after you've passed the double cover, you've actually defined a canonical, almost complex structure associated with the metric. So in fact, it's just related to the two form by index lowering, the way I normalize the self-dual two form. And the essence of the claim is that if we also have not just the determinant of W plus is positive, but the manifold is also compact in Einstein. I mean, I could have carried out some of this discussion otherwise without ever using the Einstein condition. But the claim is that in the presence of the Einstein condition on a compact manifold, this J is going to be integrable. That's the hard part of the theorem. All right, so in particular, if you put in the simply connected hypothesis, of course, that means there aren't any non-trivial double covers, and so this process really does work on the original manifold. So a corollary is that every simply connected compact-oriented Einstein manifold with the determinant of W plus is everywhere positive. Such a thing is necessarily diffeomorphic to a del Pezzo surface, and in fact, one can then see that these metrics sweep out exactly one connected component of the Einstein moduli space for that four manifold. Now, one thing that was missed in Peng Wu's original paper, of course, his argument is completely different from this. It didn't proceed in the way I've just described. But this way of thinking about the problem also emphasizes that you should think about the possibility of having to pass to a double cover of the manifold. And in fact, that turns out to be essential. So if we allow with the same hypotheses, we could allow the possibility our four manifold is not simply connected. And then it turns out that it admits an Einstein metric with determinant W plus greater than 0 everywhere, if and only if it's on the following list of diffeotypes. Well, the first one is kind of the most obvious. Take the Riemannian product of the two-sphere with itself, and then you can mod out by a Z2 action where, let's say on one factor you apply the antipodal map, and then on the other factor you just reflect through the equator. So on both factors, you reverse the orientation, but this is orientation preserving when you do it on both factors simultaneously. And because there aren't any fixed points on this factor, there are no fixed points of the involution. I'll call that manifold P. And then there's a rival. There's another quotient of S2 times S2, where you could have modded out by the antipodal map on both factors. Now, it turns out that these two guys are not diffeomorphic. When you write down two candidates like this, you might, well, maybe they're just diffeomorphic. They're not. In fact, P turns out to be spin and Q is not spin. So they're definitely not diffeomorphic. The next thing is you could take Q connected to some CP2 bar. You might say, well, what about P connected to some CP2 bar? It turns out that those are diffeomorphic. The difference in the diffeomorphism type disappears once you take a connected sum with CP2 bar. And the next thing is that you could take a connected sum of Q with 2 CP2 bars or with 3 CP2 bars. And actually, all of the Einstein metrics that you get are double covered by Kähler-Einstein metrics on del Pezzo surfaces, either S2 times S2 or CP2 connect some 3 CP2 bars, or CP2 blown up at 5 points, or CP2 blown up at 7 points, where as an algebraic variety, these are defined over the real numbers, not just over the complex numbers, but where the real locus is empty. So when you you look at some system of homogeneous polynomials and think of the locus in CPN for some n, then if they're real polynomials, that does not mean that they cut out anything in RPN. Right? So we're in the case where there are, so in particular, when you complex conjugate in projective space, it doesn't have any fixed points. And that gives rise to these anti-holomorphic involutions of the title. So I asserted that only possibilities involve Kähler-Einstein manifolds. So you're looking at this, you might think, well, there was S2 times S2. What about maybe a Z2 quotient of CP2 connected some CP2 bar? Well, if we didn't demand M to be oriented, you could do that. But it's impossible to get an oriented manifold that's double covered by CP2 connected some CP2 bar. And of course, the hypothesis assumes that we can talk about the determinant of W plus that involves an orientation. When you switch the orientation of a manifold, it interchanges W plus and W minus. So for our question, the manifold has to be oriented. So if suppose that you had an oriented four manifold that was double covered by CP2 connected some CP2 bar, then you can just, by looking at the Euler characteristic, you can read off that its second integer cohomology would be finite. The second Betty number is 0, just by looking at the way the Euler characteristic behaves. So H2MZ would be pure torsion. On the other hand, the double cover has torsion-free second cohomology. And that means that if you pull back the first Chern class of any spin C structure, you would get 0. In other words, so every oriented four manifold admits spin C structures. Pull back a spin C structure in this case, you would get a spin structure on the manifold upstairs, but it isn't spin. That's a contradiction. All right, so that was the list of the non-simply connected candidates, all of which are realized. One cute fact, since a lot of people at looking at these lectures are interested in almost complex structures, these are four manifolds that don't admit almost complex structures, even though they're double covered by complex manifolds. So the Todd genus is an index of an elliptic operator. It's the generalization of d bar plus d bar star for an almost complex manifold. And in real dimension 4, that's the Euler characteristic plus the signature divided by 4. That's also multiplicative under covers. So for a del Pezzo surface, the Todd genus is 1. If you had something double covered by it, it has Todd genus 1/2. If that's not a contradiction for a four manifold, but it's a contradiction for an almost complex four manifold, the Todd genus would have to be an integer. All right, so all of these quotients of del Pezzo surfaces are examples of four manifolds that don't admit an orientation compatible almost complex structure. I'll leave it as an exercise. Well, some of them have almost complex structures for the opposite orientation, some don't. All right, so here was a nice list. I like to classify things. And we put that together with the oriented list, and we find out that there are exactly 15 diffeotypes of compact-oriented four manifolds that carry Einstein metrics with determinant of W plus positive everywhere. And for each of these special Einstein metrics with W plus of determinant of positive determinant, these sweep out exactly one connected component of the Einstein moduli space. So part of the exercise is to look at the Einstein metrics we've constructed, and they're all, they all come from generalizations of Kähler-Einstein metrics. You can tell exactly how many we have. They come in one connected family for all of these examples. But now you want to claim that when you include them into the Einstein moduli space, that connected family is also both open and closed. So why is that the case? Well, the condition that the determinant of W plus is positive is an open condition on Riemannian metrics, and you're just restricting that to Einstein metrics. It's open. And on the other hand, one ends up showing that that W plus is very special for these manifolds. There's always a repeated eigenvalue, and so they actually satisfy two closed conditions. The determinant of W plus minus 1 over the 3 square roots of 6 times W plus cubed has to vanish, closed condition, and then also the scalar curvature is greater than or equal to 0. That's a closed condition. All right, so you can describe these either by an open or closed condition, and therefore it's an open and closed subset of the Einstein metrics. And therefore, it actually sweeps out exactly one connected component of the Einstein moduli space. Now, I said that my proof of that Peng-Wu's criterion works actually proves more. And in fact, the sharp version of my argument is that if you have a compact Einstein four manifold with W plus nowhere 0, and if its determinant W plus is not too negative compared to W plus cube, then in fact the determinant of W plus has to be positive. So if you wanted to, this indicates that there's something, thinking about the determinant of W plus is a very robust condition. You can kind of, so a priori, the determinant of W plus could be a somewhat larger a negative multiple of W plus cube. It can get about not quite twice as big as this, but this covers a lot of territory. And it indicates that this is a very promising and interesting condition to study on Einstein four manifolds. It turns out to be surprisingly rigid. All right, so let me just end with some indication of the proof. And just to keep it clear, I'm not going to use the weird condition I just indicated. Let's just assume the determinant of W plus is everywhere positive, as Peng-Wu originally suggested. So by the second Bianchi identity, one consequence of being Einstein is the divergence of W plus is 0. So when I say the divergence, I just mean take its covariant derivative and then take the trace. In fact, if you take the divergence of the full Weyl tensor, that can be expressed in terms of covariant derivatives of the Ricci tensor and the scalar curvature, so that vanishes for an Einstein metric, and then you can take the self-dual part before or after you take the divergence. It gives you the same answer. That's what on this line, I'm saying that you could either think of taking the divergence of W plus or take the divergence of the full Weyl tensor and then take its self-dual part as a two-form with values and covectors. All right, so our strategy is to study the weaker condition of the divergence of W plus being 0 as a kind of proxy for the Einstein equation. And the reason is that this transforms very nicely under conformal transformations. It's actually conformally invariant with a weight. So if your metric is written as f squared of another times another metric g, if that metric has delta W plus is equal to 0, so W plus is harmonic if you like. So here, notice I'm using the color H with the red metric. Delta here means the operator associated with the red metric. Then G instead satisfies that the divergence of F times W plus is 0. So as long as you forget that W plus is basically curvature, but you just say, well, it's a tensor field with certain symmetry properties, you get a solution of the same equation. It's just that the weight that it's transformed with is a sort of surprising one. Now, divergence of, this is saying that a self-dual form with values in a bundle is co-closed, and because it's self-dual, it's saying it's harmonic as a bundle value 2 form. So that implies a Weizenbach formula, and the shape of the Weizenbach formula is this. You find that the rough Laplacian applied to this field, FW plus, scalar curvature. So this is true for the original metric where you use the original derivative, but F would be 1, right? But now for our rescaled metric, we just have to remember to consistently put in this factor of F, which looks pretty innocuous, except here the factor of F is under 2 derivatives. All right, so here I thought of W plus, FW plus is being thought of as an endomorphism of lambda plus. And so here when I say compose W plus with W plus, I mean as an endomorphism of lambda plus. Here, the identity is the identity thought of as an endomorphism of W plus. All right, so, so we'll now choose such a rescaling of our Einstein metric that's adapted to our problem. And we'll take a certain adapted self-dual 2 form, and I'll tell you in a moment which those are going to be. So now you could take the L2 inner product of this Weizenbach formula with omega tensor omega. And now you could integrate on the manifold. And by integration by parts, you can now throw the derivatives off of FW plus onto omega tensor omega. And that allows you just to pull out this function f. In other words, you get a very nice Weizenbach formula where the only curiosity is that the volume form you have to integrate against is curiously weighted by this function f, which we haven't yet specified. In fact, when you write out the Weizenbach formula, here's what it looks like. All right, so this is a sort of general fact about Einstein metrics and conformal rescalings of Einstein metrics in dimension 4. But in our case, we assume that W plus had positive determinant. Therefore, when we looked at the top eigenvalue of W plus, that was a smooth function on the manifold. And so what we could do is take our function f to be the inverse cube root of that alpha, and take our metric to then be the corresponding rescaling. We're going to multiply the metric by alpha to the 2/3, where alpha is the top eigenvalue of W plus. Now, on the other hand, the eigenvalues of W plus carry a conformal weight. When you rescale the original metric h by f to the -2, it turns out the eigenvalues then scale by f to the +2. So actually, this is set up, so this particular choice has the property that the new top eigenvalue for the rescaled metric is f inverse. And in particular, alpha times f has been arranged to be 1. All right, so we now choose an associated self-dual 2 form of length square root of 2, which is in the top eigenspace of W plus. Now, this might involve passing to a double cover of the manifold. If the manifold is simply connected, we can do this. Otherwise, perhaps we have to pass to a double cover. All right, so we now look at this Weizenbach formula. And so we've arranged that omega has constant length, and it is in the top eigenspace of of W plus. And you notice that there are a lot of W pluses around, so that's going to have some consequences. So first I could break up that Bachner-Laplacian has been, right now it's falling on omega tensor omega. So I get 2 terms, one of which involves the derivatives of omega, and the other involves the Laplacian of omega. And then I can remember that omega has been chosen to be in the alpha eigenspace of W plus. So if you like, I could rewrite a lot of these terms just in getting rid of the W plus that appeared. And now there's a general fact about the norm squared of W plus as related to the norm, the square of any eigenvalue, simply because it's trace-free. It's not just bigger than an eigenvalue squared, but because it's trace-free, it has to at least be 3/2 the square of the eigenvalue. And so here we had a term that involved, before we had actually an equality, but the W plus squared we just said it's at least 3/2 of alpha squared. And so we have a lot of appearances of alpha here, where alpha is the top eigenvalue of W plus with respect to our rescaled metric. But now what will we do with this first term, which involves W plus acting on the covariant derivative of omega? Well, here, because we've assumed that we've set it up so that omega has constant length with respect to omega, its covariant derivative is always perpendicular to omega. And in the other eigenvalues, so omega is in the positive eigendirection of W plus. In the other directions, it's negative. So this first term is minus something which is negative. And so, in fact, since we've already made a sacrifice, this is already an inequality. This is the first thing minus this blah, blah, blah. That's already positive. We can just throw it away. We still have an inequality. And so now this inequality is starting to simplify. But remember, I also chose it. My choice of the f was that alpha times f was 1. So in fact, I can now find, I had this kind of horrible f that I didn't want to work with, but I've set it up so that it cancels. And now, by stepping back, I could write, my conclusion is that this rescaled metric actually has the property that the inner product of omega with the Bachner-Laplacian omega times 2 minus a Weyl term plus a scalar curvature term is actually a non-positive. But actually, you can rewrite that if we pull out a half of the covariant derivative of omega squared. And then remember there's a Weizenbach formula for the Hodge-Laplacian on two forms on self-dual two forms on a four manifold. This ends up telling us that 0 is greater than or equal to half of the covariant derivative squared of omega plus 3 times d omega squared. Well, I mean, that means that the covariant derivative of omega is 0. This rescaled metric has to be Kähler. And so I hope that you have enjoyed this discussion of Einstein metrics. Please enjoy your tacos.